Vanakkam. Welcome to this video on biomechanics. We have been looking at kinematics of reaching and grasping. In the previous videos, we looked at displacements or forward kinematics of 2 or 3 or 2 link chain, 3 link planar kinematic chain. We looked at these. We also looked at inverse kinematics, or when the end point coordinate and the link lengths are given, what are the joint angles. This we did for the 2 link chain. We also did this for the 3 link chain, but with an assumption that we know that the inclination of the this we did also for the 3 link chain, but with an assumption that we know the inclination of the last link, right. In this video, we will be focusing on differential kinematics. We will be performing velocity analysis. So, in the previous set of videos we have done displacements, now we will do velocity and we will define this what is called as a Jacobian matrix. So, what we know about velocity from high school physics still holds. What we know is that velocity is the time rate of change of displacement or position. It is a vector. Displacement is a vector. Velocity is the time rate of change of displacement, and it is a vector quantity. The scalar quantity corresponding to velocity is speed, which is essentially just the magnitude of velocity without direction, right. So, you need both direction and magnitude to describe velocity completely, because it is a vector. That is what we call as a vector, right. In the case of the human body, the segments or the links under consideration are all undergoing rotations, rotary motions, right. So, if objects or segments or links are in rotary motion, velocity of any point at an instant is tangential to the path of motion at the point at that instant. Why is this the case? Well, let us take a single link like this, okay. This is theta, and this theta is changing with respect to time. So, there is a non-zero theta dot, let us assume that. In that case, the question is, what would be the direction of the velocity? Note that AB itself is the length of the segment. This is something that does not change, because this is the length of the rigid body, this is the size of the rigid body. It does not elongate or shorten during the course of motion. Due to the motion, it does not change its dimensions. So, there are only two possibilities by which the velocity can change. One is along this direction, which is along AB, but that is not possible, because in this case, or in the case that we are discussing, AB is a rigid body and its length does not undergo a deformation, does not either elongate or shorten, contract, right. The other possibility is in a direction perpendicular to this, in that direction. It turns out that when this is happening, as this is rotating, right, when this is happening, let us say that it is rotating with some angular velocity omega, then you will have, because let us call the distance AB as some r, right, and because r dot is 0, r dot means, let me rewrite this, dr by dt is 0, that is, with as a function of time the distance AB does not change, that is what this means, right. But omega is not 0, right, theta dot or omega is not 0, right. So, when that happens, there is only one way, one direction in which the velocity can change, and that is in that direction or perpendicular to the link at that point. And note that the link itself can be in a different position at a different point, and at that point the velocity will be in a different perpendicular, right, in that perpendicular, right. So, at any point, right, the velocity of this rotating body at any instant of time will be tangential to that point at that instant, because at a different instant the point itself would have moved, and at that point, at that instant, it will then be tangential. So, this is something that keeps on changing, right. So, we are interested in performing kinematics analysis or differential kinematic analysis or velocity analysis for 2-link kinematic chains and 3-link kinematic chains. But before we do that, let us look at how it would look in a single link. Okay. Let us assume that we have a single link like this. So, I am going to erase all this that I have written. Okay. Let us assume there is a single link, and the angle is theta. Okay. The link length is some L or R. Okay. It is rotating with uniform angular velocity. So, angular velocity does not change. In other words, alpha is 0, alpha is omega dot, and that is 0. Okay. It is having uniform angular velocity theta dot or omega, which is not 0. With some uniform angular velocity at this instant. The question is, what is the velocity of point B of the tip or of the end effector? Given that I know the link length and I know theta, I know theta dot. Let us assume that I also know omega, I also know, this is also known. I know the uniform angular velocity, I know the theta at that instant, I know the link length L. The question is, what is the velocity of the end effector or the tip of this link point B? That is the question. Well, first I can write out the coordinates of the point B. Okay. The x coordinate of point B is from our vector analysis, that is L cos theta, and the y coordinate is L sin theta. We know this. How do you know this? We have done this previously from our previous analysis of vectors and also in analysis of statics. So, that is the coordinate. Bx is L cos theta. Okay. Likewise, By is L sin theta. Okay. I am saying let us differentiate this with respect to time. Well, normally if L was not a constant, you would use chain rule. That is, you would first assume L as a constant and differentiate the other quantity, then keep the other quantity constant and change L. This is what you would do. But then L dot is 0, that is L does not change with respect to time, L dot is 0, right. So, I could change this. So, I could differentiate because L dot is 0. So, I am not even considering that part, that term in the chain rule. I can simply write this as L times d by d theta of d by dt of cos theta. Is it not? This would be L times minus sin theta. No, this is not correct. Let me formulate it again because it simply says Bx. Okay, let me write this out. So, then the velocity Vx would be L times the differential of cos theta, that would be minus sin theta times d theta by dt, is it not that, and Vy L times cos theta, because differentiation of sin theta is cos theta times d theta by dt. D theta by dt, we simply use the notation theta dot. So, this is minus L sin theta theta dot, and this is simply L cos theta theta dot. Is it not? Now, we know that theta dot is moving perpendicular or tangential to the segment, to the link itself, right. So, that is the direction in which this will be, right. The magnitude of this velocity will be L times, well, there are two components obviously, there is a Vx component and there is a Vy component. The resultant of these two velocities will be perpendicular, that is V, right, that will be along a direction that is perpendicular to the link itself, right. Now, with this done, let us move on to the case of a planar two link serial kinematic chain, right. What we know from forward kinematics is, the end point is L1 cos theta 1 plus L2 cos theta 1 plus theta 2. How do I know this? Well, this is what we did in the previous videos. Essentially, I said this is the coordinate of the end point P, x and y coordinate of the end point P, right. Y is L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. This is also something that we know from the previous analysis, right. I am going to use this notation. C1 is cos theta 1, S1 is sin theta 1, C12 is cos of theta 1 plus theta 2, S12 is sin of theta 1 plus theta 2. Okay. So, essentially rewriting this one more time, x is L1 C1 plus L2 C12, y is L1 S1 plus L2 S12. This is what we have. Okay. Now, what I do? I simply differentiate these two equations with respect to time. Okay. If I differentiate the first equation with respect to time, on the left hand side I will get, well, I will get dx by dt, which is x dot. I will write this out in the next step. Dx by dt is L1 itself does not change, but cos theta 1, because theta dot is involved, cos theta 1 will have a differential. L1 does not change, that would be L1 times minus S1, is it not? L1 times minus S1, that is what we saw in the previous step, the previous slide, right, because the differentiation of cos theta is minus sin theta, minus S1 times theta 1 dot, is it not? Because there are two thetas here. Earlier there was theta 1 only, there was only one theta. Now we have theta 1 and theta 2. So, this is L1 times minus S1 times theta 1 dot, or rather d theta 1 by dt that is the first term, differentiation of the first term. The next term again L2 does not change, but C12 will change, right, plus L2 times minus S12, L2 times minus S12 times d theta 1 by dt. But then we realize there are two thetas that are involved, which will have to be differentiated using chain rule. Now, let us take a few seconds, let us take a brief detour and come back and do this. Okay. So, now I have S12, which is sine of S12 is sine of theta 1 plus theta 2. Considering that both theta 1 and theta 2 are changing, I am interested in I mean C12, right. Now look at, now let us consider C12, which is cos of theta 1 plus theta 2, considering that both theta 1 and theta 2 are changing, and I am interested in differentiating with respect to all thetas, is it not? They are all changing with respect to time. So, I am interested in differentiating this. What would I get? Well, differentiation of this, whatever that is, would give me minus sine of theta 1 plus theta 2 times theta 1 dot, that is d theta by dt, d theta 1 by dt minus sine theta 1 plus theta 2 times d theta 2 by dt. Now, where did this term come from? Because theta 2 is also changing. First, I differentiate with respect to theta 1 and then with respect to theta 2, is it not? So, essentially there is a d theta 1 by dt and then there is a d theta 2 by dt, because both theta 1 and theta 2 are changing. Because of this reason, this differentiation will have one more term here. Coming back to the original differentiation of dx by dt, I will have L2 times minus S12 times d theta 1 by dt plus L2 times minus S12 times d theta 2 by dt. Is it not? We will have to do this patiently. This is not rocket science, I understand that, this is high school, which is why this is harder to do. So, we will have to go back to the basics, we will have to go back to our foundations and do it patiently, step by step, one little baby step at a time. Now, dy by dt. Now, let me rewrite this before I proceed to dy by dt. This is not erasing, is it? Interesting. Okay, let me rewrite this. This is minus L1 S1 times theta 1 dot plus or rather minus L2 S12 times theta 1 dot minus L2 S12 times theta 2 dot. Now, because theta 1 is common between this, I am saying minus L1 S1 minus L2 S12 times theta 1 dot minus L2 S12 times theta 2 dot, right. This is dx by dt, or rather x dot, this is x dot. Now, the question is, what is y dot? Similar, L1 S1, if I am differentiating, I will get L1 C1, L1 C1 theta 1 dot, is it not? L1 C1 times theta 1 dot. So, I am writing this y dot as L1 C1 theta 1 dot, L2 S12, because there are two signs that are involved, sine of theta 1 plus theta 2, is it not? Now, that differentiation will have two components, there will be a theta 1 component and then there will be a theta 2 component. Now, I will differentiate that, that will be L2 C12 theta 1 dot plus L2 C12 theta 2 dot. Why? Because there will be two thetas, theta 1 and theta 2. Using chain rule I will get theta 1 dot and theta 2 dot. Now theta 1 dot is common between these two terms. I can take this as L1 C1 plus L2 C12 times theta 1 dot plus L2 C12 times theta 2 dot. So this is the differentiation of the y component, right. So this is y dot. Now I can write out the entire equation as a matrix. Now I can write out this entire velocity equation as a single matrix. Let me try to write this out. This is velocity, right, which is x dot y dot. Okay, this is going to have coefficients minus L1 S1 minus L2 S12 minus L2 S12 L1 C1 plus L2 C12 L2 C12 times theta 1 dot and theta 2 dot. Is it not? Now if you perform matrix multiplication in the usual method, there is only one correct method to perform matrix multiplication, you will realize that this is essentially the equations for x dot and y dot written in matrix form. Now let us I will just take a break and see what these the future this. So this is what he has done. Okay, from now I can simply move on to the next slide.
No need of writing anything.
Yes, I guess so. That's what I wanted to make sure. Otherwise I will be writing out the entire thing. So let's take a few seconds and examine this situation a bit more closely. The column vector on the left hand side, that is x dot y dot, which is this. What is this? This is the velocity of the end point, right. This is the velocity of the end point, or rather the linear velocity of the end point, right. What is the column vector on the right hand side? This is the joint angle velocity or angular velocity of the joints, of the individual joints. Remember, these are two different things, right. One is this point velocity, linear velocity of that point P, whereas theta 1 dot, theta 2 dot are these two quantities. Not this matrix here somehow miraculously relates theta 1 dot and theta 2 dot to x dot and y dot, or in other words, if I know theta 1 dot and theta 2 dot, this magical matrix can transform it to x dot and y dot, right. So that means that this should have some special property, like how is this even achieved, right. This 2 by 2 square matrix, by the way, this is a square matrix in this case because we are considering a two link chain. So it is a square matrix in this case, it need not be square. This 2 by 2 square matrix essentially relates joint velocities to endpoint velocities, right. This matrix is called as a Jacobian. This, let us move on. So this is the situation one more time. In this, x dot y dot is the end effector velocity, theta 1 dot, theta 2 dot is the joint velocity. The matrix in the middle is the Jacobian matrix. The Jacobian matrix, how is it obtained? it is attained when you differentiate a vector, or rather when you partially differentiate a vector with respect to another vector, So, this matrix is the matrix of partial derivatives that does not depend on the endpoint or the angles. It depends purely on the configurations. It does depend on the thetas, but not on theta dots. It does depend on x and y, but not on x dot and y dot. Okay, so it depends on the configuration, but not on anything else. So it's a matrix that is purely defined by configuration of this kinematic chain, right, based on that. So that means that for different configurations you will end up with different Jacobians, but you can compute all of them, pre-compute them. For example, a different config, because there are only, if there are a limited number of configurations, for example, if there are a limited number of configurations, then I could practically compute all these possible Jacobians ahead of time. So as soon as I have theta 1s and theta 2 dots and theta 1 dots coming, I can quickly compute x dot and y dot, right, of course dependent on the configuration, something to keep in mind, right. So the general form, right, so what is this? So this Jacobian is a geometrical mapping matrix between joint motion, which is theta 1 dot theta 2 dot, and effector motion, which is x dot y dot, right. So it provides a mapping, it is a mapping matrix. So this is the partial derivative of the position vector with respect to the joint angle vector. There are two vectors, right, position vector and the joint angle vector, defined as dou x1 by dou theta 1. So that is dependent on theta 1s, and then the next column will have dou x1 by dou theta 2, and so on and so forth until theta n, right. The second row will start with dou x2 by dou theta 1. So that is for the second x, and so on and so forth. This is purely dependent on configuration and not on theta 1 dot and theta 2 dot and so on and so forth, right. It is a configuration matrix that is used for mapping between the joint space or joint motion space and end effector motion space. Very, very convenient use for this. So for a 2R manipulator, simply this will be the Jacobian matrix, right, dou x by dou theta 1, dou x by dou theta 2, dou y by dou theta 1, and dou y by dou theta 2, right, which is what we would get, because if x and y are L1 cos theta 1, L2 cos theta 1 plus from first principles we already defined it and we found this matrix, but it is indeed easier to do this by using the matrix of partial derivatives, which is the Jacobian, using this formula, right, dou x by dou theta 1, dou x by dou theta 2. If there is one more link, then there will be a dou x by dou theta 3, and so on and so forth, right, but that will not be a square matrix, of course that will not be a square matrix. Now I have a question. Oh, he is moving to 3 link chain, is it? Now I have a question. Let us say that I know the endpoint velocities. Okay, in many real world problems I know the endpoint velocity, and I am interested in finding the joint angle velocity or the angular velocities theta 1 dot and theta 2 dot. Is it possible to find it? Well, mathematically that does not look like a very difficult problem to solve. All I need to do is to take the inverse of this Jacobian and then multiply with the x's, right. That should be straightforward, except of course inverse is defined only for square matrices mathematics, right. Inverse is defined only for square matrices. So I can do this properly only in this case. Of course I can do this properly because this is a 2 by 2 matrix, a square matrix. I can of course find J inverse and then compute. So in other words, can I perform inverse kinematics analysis using this Jacobian matrix? That is the big question. The answer is yes, I can do this. So in other words, if I know x dot and y dot, and if I have the Jacobian, I can use, simply use inverse Jacobian to find out theta 1 dot and theta 2 dot. Straightforward application of matrix methods. that will work in this case because J is a 2 by 2 matrix or a square matrix. But there are not many cases in which, in fact, other than this, perhaps all the multi-link planar chains, for example, will not have a Jacobian that is square, because it is a planar chain. There are only two coordinates that are involved, and there will be multiple thetas that will be involved, theta 1, theta 2, theta 3, theta 4, theta 5, theta 6 and so on. In the planar case, even if you take a spatial case, even if you take a 3D case, then it is square only for the case with 3 links and in 3D, right. Of course, that will be a lot more complicated, but that will only be the only square matrix. There will be no other square matrices. How do you solve this? That is the question. Something to keep in mind. Okay. Anyway, the point is that if I had a 2-link planar kinematic chain whose endpoint velocity are known to me, I could compute the joint angle velocity simply by finding the inverse Jacobian. That is straightforward. Now, let us proceed and try to do, can we record this as a separate video? So, with this we come to the end of this video. In this video we saw differential kinematics, in particular the kinematics of 2-link serial kinematic chain. So, in other words, finding the endpoint velocity as a function of the joint angle velocity analysis, and we defined a special matrix called as the Jacobian matrix, the matrix of partial derivatives that depends on configuration and helps us to geometrically map from the joint angle space to the endpoint space, right. So, joint angle motion is described in endpoint motion. So, joint angle motion is used to describe endpoint motion. So, with this we come to the end of this video. Thank you very much for your attention.